Okay, so we've talked about how velocity can be described as a position versus time graph. So there's our XY graph, so we're actually going to put X, or position or displacement, on the Y-axis, and time is on the X-axis right here, and so you can have graphs that look like that, or like that, or like that. Now we're going to talk about how, oh, by the way, and of course, the slope at any one time is the velocity, because velocity is described as position over time. Now we're going to talk about how acceleration is a change in velocity over a change in time. Let me just go ahead and I'm going to delete this right here because that doesn't pertain to this section. So this section is velocity, or change in velocity over a change in time. Okay, so you have a graph that looks like, I don't know, like that. All right, well, what is your rise over your run? Well, that's velocity over time, right? And we know that to be acceleration. So if this were to be, actually the good news is we're not going to need to worry about this, the secant line or a tangent line, too much. It'll make sense in just a second, but the line that I drew, you can't really draw a secant line of a straight line because the secant line is a straight line connecting 2 points, and so that would just go right over top right there. And you also know that a tangent line is a line that is, well, it is the slope of the line at any one point. Well, the slope is all the same. So the secant line and tangent are not really important to this graph that I just drew right here. If we were to have a graph like this, where you've got, now remember, this is velocity over time, so the slope is going to be acceleration. Here you have a high acceleration, and here you have a less acceleration right there. I didn't mean to draw that arrow shorter. I just meant that, in fact, I'll just erase it and draw it the same length, but it's a less acceleration because it's less of a slope. Then you could draw a secant line. And so between 2 points, that is, between any 2 points in time, the secant line would represent the average acceleration between here and here. Because again, it's that change in velocity over change in time. Like I said, the good news is that we're not going to be dealing too much with changing accelerations, a high acceleration and a less acceleration. A change in acceleration is something that we call jerk, and it's like what happens when you rear end somebody in your car and your head goes flying forward because you're slowing down very, very rapidly, and actually you're decelerating at a very fast rate all of a sudden. We're actually not going to deal with that. In the same way, since we have these tangent lines right here, we don't need to worry about tangent lines if we have a constant acceleration, because like I said before, the secant line and the tangent line are the same thing. So the good news is for us that we're going to be dealing with constant acceleration class. So let's look at this right here. This is a good example of what we would actually see. So here we have a velocity over time graph. Now the velocity goes positive and negative, okay? And then we've got time that just goes positively right here. So the question is, what's happening to this object in the picture? Okay, so we have 4 graphs. We have A, B, C, and D. So don't freak out that that we might see graphs that look like this. No. These are 4 different graphs, but we just put them all on the same axis right here. So let's take a look at this. All right. So what's happening with A? All right, A right there. I'm going to do these in different colors. So A, first of all, initially, it has a positive velocity, right? Because this is the positive direction, and that's the negative direction right there. So it has a positive velocity, and what's our velocity over time? That's acceleration, right? What kind of slope is that? That's a positive acceleration. It's a positive slope going up like that. So it's moving positively and accelerating positively. All right, so it's going faster and faster in the positive direction. Okay? Let's look at the second one right now. I'll make this one blue. All right, the second one, it starts with a positive motion, all right, a positive velocity right here. So I'm going to write that right away. It's moving positively. But look what happens. The slope of this line, this acceleration, this change in velocity over change in time. Look, it's got a negative change in velocity. So the velocity must be decreasing, or that is, it's getting less. It's accelerating negatively, right? Or actually it means it's decelerating. Because look, the velocity, what velocity is now on the y-axis right here. This velocity that was so big, over time the velocity is getting less and less and less and less. And it's actually approaching zero. So it's coming to a stop because it has a negative acceleration right there. Okay, let's look at C. C, I'm going to make green. All right, so here we have an object that starts initially, it's got a negative velocity, right? Negative velocity right here because it's below the line. So it's moving negatively, but you can see that the slope of the line, the slope of this change in velocity over change in time, it actually has a positive, Koa, please be quiet. Sorry, that was my dog in the background. It's got a positive change in velocity over time, which means it's not going quite so negative as it was before. Basically means it's, if it's accelerating positively, that means it is decelerating, oops, E-R-A-T-I-N-G, because it was going negatively, but it's coming to a stop. All right, it's approaching zero. So you hear this negative velocity. So it's like you're going backwards, but I'm slowing down, and eventually I'm not going backwards anymore because I'm coming to rest. I'm coming to zero velocity right there. All right, and finally this last one, let's make that, I don't know, pinkish or something like that. All right, so right here we're starting with a negative, moving negatively, and look, we have a negative change in velocity, or negative velocity change over time. So it's actually accelerating in the direction it was going, but it's accelerating negatively. All right, it's going faster and faster in the negative direction because this negative acceleration is, you might say, enhancing the negative velocity that it had right there. So these are 4 different possibilities that you can have. So it is certainly possible to have an acceleration and yet be coming to a stop, because if you're going backwards but you have a positive acceleration, you're actually approaching zero velocity. And then you'll probably start moving forward after that. So if we look at these graphs, they tell us a couple different things. All right, I think we pointed this out before, that on a position versus time graph. All right, so there's position and there's our time, or displacement versus time, I should say. All right, the slope equals the velocity. All right, so right here we've got a high slope, we've got a negative slope, and no slope right there. So the velocity is changing. We can do that. But what if we have a velocity versus time graph? What this means, the area under the curve equals the displacement. And I'll point that out in just a second on this very next slide. All right, if we have an acceleration versus time graph, oh, I'm sorry, I didn't want to do that. A velocity versus time graph. All right. If I could just drew that, I could have just drawn on it before. The slope equals the acceleration. All right. Well, so that means I should have just drawn it up here. We have a constant slope, which means a constant acceleration. That's good. We don't want changes in acceleration. That's for a different kind of physics class. All right. So this slope right here, and by the way, the slope is the same all along here. So of course it's going to be constant, right? And here we go. This is what I meant to do before. On an area, or sorry, on an acceleration versus time graph, the area under the curve equals a change in velocity. I'm going to point that out in just a second. All right. So let's go. I'm going to look at this. All right. So we have something that is going a certain velocity, and then it accelerates. See, we have a constant slope right here. That right there, it's a constant slope. Here we have velocity over time, and on a velocity over time graph, what do we call that? That's called acceleration. So the slope is acceleration right here. We have a constant acceleration. This object goes from 1.5 meters per second to something much faster, 13.5 meters per second. All right? So we know that change in velocity over change in time is acceleration. But what's this whole area business we're talking about right here? All right? Well, remember, area, if you want to find the area of, let's just say, let's make it easy. All right? Let's say the acceleration didn't even change, but it was just a constant velocity all along here. All right? So 1.5 meters per second for 5 seconds. How would you find the area of this right here? Well, you take the area. To get the area, you would take this change in velocity times the change in time, right? So V times T, velocity times time. Why does that sound familiar? Oh, it sounds familiar because we know that is displacement, right? So, like, remember we said that velocity is change in displacement over change in time. Well, we just brought the T up and multiplied it next to the velocity. So if we multiply on a velocity versus time graph, if we multiply velocity times time, that gives us the displacement that this object underwent. Even if the velocity changes over time, if we have an acceleration, that's okay. You guys know how to find the area of a triangle. All right, it's just 1/2 base times height. So if you have it moving at this velocity, all right, and then it goes faster, for these 5 seconds, you would get this area plus this area, and that would tell you the displacement that thing has undergone. You wouldn't even need to do the one of the equations. You could simply find the area underneath this graph right here. We call it the area under the curve, not all graphs. We can call it the area under the graph. All right, so 2 guiding equations for position versus time, or I should say displacement versus time, and velocity versus time. All right, remember this one? This is our equation number 4, I think we called it. So we're saying the displacement, and if we were just to take, come on now, there we go. If we were to take this initial position and bring it over there, that would be x minus x initial, or that is our change in x, our change in displacement. Okay? So anyway, the reason we have that there is because this is saying that x, which is on the y-axis, depends on what t is, depends on what time is right there. All right? Now this is a quadratic equation, which means, can I erase that? No, I can't. I'm going to have to do this, that little red thingy right there. Which means you might need to use the quadratic formula if you're solving for time right there. But it also means that you could have a parabola, right? You can't have a parabola. Let's see. Position versus time. Oh, that's not time. It's a V. Position versus time right here. You can't have a parabola without something being squared, right? So if we had a graph like that, then that would mean that there would have to be some sort of acceleration because the velocity, that is that slope right there, is changing. A change in velocity is the definition of acceleration. Right? If you have no acceleration at all, if there's no acceleration, then the equation becomes linear because the acceleration, this whole thing right here, that t squared, is what makes the graph curved. But if there is no acceleration, then it becomes a very, very neat looking graph. If, however, we have a velocity versus time, or velocity versus time graph, we know the slope of that is acceleration, and it will always be a straight line because, like I said before, acceleration is always going to be constant, all right? And so we're going to have a linear relationship right here. If you were to take this v final and v initial and take that v initial and bring it to the other side, you would really have v final minus v initial, or change in velocity, okay? And acceleration, I'm going to write this at the bottom right here, acceleration is a change in velocity over a change in time. All right, so this, I'll write this in green, change in velocity over change in time. That's going to result in a constant acceleration. It's not very evenly drawn arrows right there, but you get the idea. The constant acceleration is indicated by a straight line. What if there is no acceleration? All right. Like I said, I'm not going to go back to the previous slide, but on the previous slide, remember if I said, let's pretend there's no acceleration, and I drew that line straight across like that. All right. It had some initial velocity, and the final velocity was the same thing as the initial, but the flat line, the horizontal line, indicated there was no acceleration. There was no change in velocity over time. It was just a constant velocity. That's what this last little point indicates right here. So in the next video, we're going to actually practice doing some graphs and seeing what these graphs look like. But for right now, these two equations, equation 4 and equation, I believe we called that number 1, are your two important ones to really kind of decide what the graph will look like if we're comparing position versus time and velocity versus time. All right, I'll see you on the next video.